So this was the definition of frames and parameters. There are some left ambiguities in the definition which mainly concern the initialization of this recursion, so the base frame, and the last frame. Why there are these ambiguities? Because we have seen that the definition of frames goes through the definition of common normals, and if we have the link 0, where the frame 0 is placed, we have joint 1, but we don't have joint 0 to define a common normal. And similarly, for the last frame attached to link n, we have joint n, but we don't have a joint n plus 1, so we cannot define a common normal. So the idea behind completing this frame, so frame 0 and frame n, will be to be as much as consistent as possible with the other definition, and in addition, frame 0, the degrees of freedom that are left guide us through the fact that everything will be defined in this frame, so we will choose it in the most convenient way, while for frame n, we will try to put the origins of frame n, if this is possible, located in the place for which we want to compute the position, so that the main position of interest will be the origins of frame n. So, in particular, for frame 0, the z0 axis is defined. Why? Because it's along joint axis 1, so the first joint axis of the robot. What is not defined is the axis of the link 0, so the common normal is not there, so the x0 axis will not be defined, and the origin as well. So we can arbitrarily choose this in the most appropriate way, and we will see an example later on. Similarly, for frame n, what is not defined is Zn, because Zn should be on joint n plus 1, which is not there. But so we can arbitrarily define this Zn, but we need to define xn of this frame so that it intersects and is orthogonal to the last joint axis defined, so to the joint axis n, where Zn minus 1 is placed, so that we mimic the presence of a common normal, and there we put xn. Out of this, Zn is arbitrary, and the origin also is arbitrary. I never talk about the y-axis, because once we have defined 2 of the 3 axes, we complete it in a right-handed way. Okay. Then there are more subtle ambiguities. For instance, when 2 joint axes are parallel, 2 consecutive joint axes are parallel, we know that we place on top zi minus 1 and zi if these are joint I and joint I plus 1. And the common normal is not uniquely defined, so there's no point of intersection, or we can define the point of intersection where we wish. So this origin OI can be chosen arbitrarily. And we typically try to define the frames when we have some degree of freedom, so to eliminate as much parameter as possible. So if we can, for instance, for we have an AI parameter, we can put this to 0, then we will put it to 0. We will place the frame so that we put this number to 0 and not to 45, just because it's irrelevant. We know that it will be irrelevant, so it is not useful to introduce data that we have then to eliminate in the computation. Okay? And similarly, when the 2 axes are incident, we know that there are common normals, and then we have to choose. Well, there is one common normal, we have to choose in which direction to take it. And for instance, you can take it in the direction of the vector product. So you have zi minus 1 and zi are on joint I and joint I plus 1. These intersect. So on one there is zi minus 1, on the other is zi, even if they are not orthogonal, they are in the same plane, so the vector product will be out of plane common normal, and in this direction you will place also xi. This is just a choice. You can do whatever you wish, but it's good to use the same rule through the chain so that you don't get lost in single choices which are not consistent, although allowed. So, now that we have defined how we moved from one frame to the other, we can associate homogeneous transformation. Now remember that we have to do 2 rotation and 2 translation for superpose frame I-1 to frame I. And as a matter of fact, a pair of rotation and translation is defined on some z-axis, and another pair is defined on some x-axis. The only care we have to take, and in this sense the previous video was incomplete, is which index carries those axes. In fact, the first is a rototranslation around rotation and along translation, the zi-1 axis. So the z-axis which is placed on joint I. Okay? So we translate by a quantity di, and we rotate by an angle theta I. So these 2 elementary things are represented by homogeneous transformation matrix. See, this is a translation because there's no rotation, it's the identity. The last row is always 0, 0, 0, 1, and this is a translation around the current z-axis, which is zi-1. And this is no translation and a rotation around the current z-axis, which is zi-1. Now, since this rotation and translation occurs along and around the same axis, it is not important the order in which you do this operation. So I can do first the rotation and then the translation, or interchange this, first the translation and then the rotation. I will always get, you can check this, the same result. Okay? And this is 1/2 of the transformation, because now we have another rototranslation around and along the x-axis, but now not the I-1 x, but the xi axis. Oh, by the way, before doing this, in these 2 products, I recognize that there's a theta and d, and I know that d is constant if the joint is revolute and theta is variable, or vice versa, if the joint is prismatic, theta is constant and d is the variable. So for each joint in this product of 2 matrices, there will always be the single variable that we use for the joint. And in fact, and here is the change of notation, this is why I'm using q. So here we have theta I and di. Now we will call, for a prismatic joint, di will be the joint variable, called qi, and theta I will be some constant. For a rotational joint or revolute joint, theta I will be the joint variable qi, and di will be a constant. Okay? So in this first part, we have the joint variable for that particular joint. Now the second combination of elementary operation is a rototranslation, so a rotation and a translation around and along the xi axis. They have exactly the same form as before. So there will be, I can write it here on the blackboard, it's just the result, because even in that case, there is no order. Any order is okay. So I will have a translation around the current x-axis, which is at this point already xi. So I will have ai, 0, 0, and no rotation. And then rotation around xi. So again, the last row is 0, 0, 0, 1. There's no translation, so 0, 0 here. And then the elementary rotation around the current x-axis, which is xi, has a 1 here. And then by an angle alpha, and there's 0, 0 here. And here all what is not there is a 0. Okay, if I do this product, or if I interchange this, I obtain this second homogeneous matrix. The final Denavit-Hartenberg homogeneous matrix will be the product of this times this. Pay attention that this second is always a constant matrix because it contains alpha and AI, which are always constant parameters. Okay? Before moving to the final result, let me write this matrix in the following way. The first one is T rot by theta I on top left. Then I have a T translation by DI. And then I have a T here, translation by AI, and then a T rotation by alpha I. So I have defined on top this product, and then this product. And then I have said that these two can be interchanged because they are both along and around Zi minus 1, so the common axis. And also these two can be interchanged in order because they are both along and around the same axis, which is xi. Okay? So I can do multiple things, no? Just to reasoning about this product of homogeneous transformation matrices. So I can write translation rotation or rotation translation like this. I can write translation rotation or rotation translation, but I will keep it like this. Now I see here there are two contiguous things, a translation and a translation. Can I interchange it? Can I place this here and this here, even if they are around different axes? Can I exchange the order of two translations along different axes? Do they commute? Yes. If I'm going from here to that angle, if I move first here and then first there and then there, is exactly the same thing as moving first here and then going there. Okay? So translation always commutes. Rotation do not commute. So there's no sense of doing this. It's just to reasoning about, it's just an exercise. I could exchange this to translation and I will obtain the same result. What I cannot do is exchange this, so I have translation rotation, which is fine because they are both around and along the same axis, and exchange this, which is fine, and then I have the two rotation matrix contiguous. Now I cannot exchange them because they are not around the same axis. Then I will make a mistake. So there are some freedom. This is why it's nice to say roto-translation, because I don't care which is the order, only because it's around and along the same axis. Okay? Same as that. And now I make the product of this times this, and pay attention how I define those A matrices, which are homogeneous matrices. This has a superscript I minus 1, because I'm starting from frame I minus 1. And I have to go to frame I. But in order to go there, I have decomposed this in elementary operation. So I'm going first to an intermediate frame I prime, which is placed at the intersection point between the first joint axis and the following common normal, and has already some orientation, so that xi minus 1 now, after these two operations, is aligned with xi. Now I have only to translate along xi and then twist so that the zi is reached. And so from this intermediate frame I prime, I go to I. Now I do the product of this matrix times this matrix. This carries no dependence because it's a constant matrix. This carries a dependence on qi because either one or the other of the parameters are variables. Okay? So when I do the product, I will have ai minus 1I as a function of qi, and this is called the Denavit-Hartenberg matrix, okay, and has this structure which is once forever. It's all that you need to take home from this long lecture is this transformation matrix, which is written in terms of the 4 parameters. Di is here, ai is here, theta is both here and in the rotation matrix, and alpha is only in the rotation matrix. Okay? So if I characterize a robot, I characterize how the joint axes are placed in space, and thus the common normal, and thus the 4 parameters for each passage from one frame to the other. So if the robot has 4 degrees of freedom, I will define, I have 5 bodies, remember, link 0, the base, then link 1, link 2, link 3, and link 4. So 5 bodies with 4 joints in between. So I need to define 4 transformation matrices. And for each transformation, I have to define these 4 parameters, one of which will be a variable. But all I need to do is to build up a table of those parameters and characterize which is the variable, and then fill in this matrix. So if I have alpha 3 is 0, and this is A3 or A23, so here I will put 0 because sine of 0 is 0. Here I will put a 1. Here I will put 0. Here 1, and so on. Okay? Very convenient, because this is now for any possible kinematic structure, no matter how funny are the joint axes placed. Okay? Now, pay attention to this notation that we are using. I have already used this here. So we compact the sine and cosine with an S or a C, and if this is of different angle, I will keep the angle in place. But later on, when I have only variable qi, for instance, I will also use this notation, ci and si, which means cosine of qi and sine of qi, because there's no possible confusion. I'm talking about all the same kind of angles, so q. If there's no possibility of confusion, then you have even more compact than cosine of c of theta I for cosine of theta I. Just write ci, okay, or si. This makes more compact, long expression. So, and now we're done. So take your favorite robot for which you want to describe the direct kinematic in the most traditional way. So you want to go from one base frame, fixed forever, there, to some end effector frame which is attached to the gripper and moves together with the gripper. Okay? So these are the 2 extreme. I'm now embedding everything in the most general case. So you have RFB and RFE, base and end effector. And you have indeed some frame, some axis. And if you forget about the robot, in order to position and orient that frame, you will need a homogeneous transformation matrix, which is not without cause, written like this, T superscript B subscript E, because this characterizes position and orientation of E with respect to frame B. Okay? And in particular, its inner structure is a rotation matrix and a position vector. This position vector goes from the origins of B to the origins of E, and the rotation matrix contains in the columns the directional cosine of the x-axis, the y-axis, and the z-axis of frame E when expressed in frame 0. Okay? So this is something that we know, and in particular we use also this notation sometimes. So the columns of R are called NSA, simply because for this standard industrial situation where you have a gripper that approaches object, the z-axis of the end effector frame is taking along the approach direction. This is why the third column is called A, because it's ZE. Then you have the second column is called S, and is where the axis YE is placed. If you have a gripper that open and close, this is the slide direction of the gripper. Okay? And then the third axis, we have defined Z and Y, so X is such that the 3 is a right-handed frame, so it's sum normal to both of them. Okay? So this is just a matter of notation. So if we don't have the robot, I know that this transformation is represented by this quantity. Now, I can also extract from here some array which is my task vector. For instance, the most simple thing is I can take the 3 component of P, and this will be R1, R2, R3, and then I can extract from the rotation matrix, so from this part, 3 angles of a minimal representation, let's say Euler ZYZ or roll pitch jaw in the sequence YXY, okay, and put them here as the other 3 component of R. So this is the standard way to representing direct kinematic in terms of position and orientation of the frame, but from this we can extract what we need. For instance, I don't care about the PZ coordinate, I don't put it here. I have it here, but here I just take out what I need, okay? So this is the so-called external to the robot description, because we are passing out of the robot, but of course, and we learned that this is one of the convenient way for doing things with homogeneous transformation, I can go from frame B to frame E, passing through the robot. So the first things, I will have frame attached to the robot, and here I show only the first frame. And the first frame is attached to the base of the robot, so it's not moving. The only thing that is defined here is the zeta 0 axis, which is around the first joint axis. Now I'm assuming that this is a robot placed on the floor, and the first rotation is this rotation. So zeta 0 is going there. Otherwise, would go in the direction of the first joint axis. So you see, in general, this frame 0, which is at the base of the robot, may not be coincident with this base frame of reference. I have added some degree of freedom. But pay attention that this is fixed, so the transformation from here to there is a T matrix which is constant. And it has no parameter, Denavit-Hartenberg parameter, because this can be placed as I wish, and this is placed also as I wish. So there are 2 frames not linked in any sense, so I need the full transformation matrix to characterize pose of one with respect to the other. Okay, then I have this frame, and then inside I have all those other frames of Denavit-Hartenberg placed according to the rules. And so for the robot, I'm characterizing its configuration with n variable, q1 to qn, because there are n joints. And now I know how I choose this variable, because this will be either theta I if the joint I is revolute, or di if the joint is prismatic, defined as in the rules and notation and convention of Denavit-Hartenberg. According to this, I can build n transformation, homogeneous transformation matrix A01, which is a function of the joint variable Q1, prismatic or revolute that it could be, then A12 function of Q2, and so on until a frame n, which is attached to the end effector, and in principle may not coincide with the end effector frame. Is on the same link, but like here, they are both on the base, but they may be displaced. So I need another transformation which is constant to bring the nth frame of the Denavit-Hartenberg notation into the end effector frame. So putting all together, I have this identity. So the external representation TBE is equal to the internal, which has a constant homogeneous transformation matrix for going from B to 0. And then I start with the standard direct kinematics until frame N, which is placed somewhere, move like frame E, but it's displaced in position and in orientation. But it's a constant change, which can be represented by another constant homogeneous transformation matrix from N to E. Okay? Now, you see that this is the direct kinematics. This is the conventional one using homogeneous transformation matrix. But if I want to extract from here some task variable R, I do the same here. So that R, the M variable, I extract from here. And then I do the same on this side. And this will provide me the direct kinematic function as a function of Q1, Q2, Qn, which is represented by some vector Q. Okay? And this is it. Now let's do one example. The example is on the SCARA. Here on the right, there's a SCARA built by Sankhyo. This is out of production now. I found a video not of this SCARA, but of a very similar one, still by Sankhyo. You see, it's the same kinematic. It has only some passage of cables outside, but otherwise it's really pretty the same. And here you see some elementary motion of only the first and second joint, so the shoulder and the elbow. Okay? Now, the additional one are the prismatic joints, which let this part go up and down inside the guide, and then the final rotation here. So the first thing to do is 4 degrees of freedom. I need 4 variables. First will be some rotation around the first joint axis. The second will be some rotation around the second joint axis, shoulder and elbow. The third will be some translation around the along the prismatic axis, which is coincident with the revolute joint axis of joint 4, around which I rotate the final flange, where I can put a gripper and reorient. Not arbitrarily, but around some axis. Okay? So, first step. For any robot, this is now shown for this simple case. Look at the joint axis, how they are placed. So if you have a data sheet, you look here and you see joint 1 is vertical. All these SCARA are mounted always on the floor, so they are never mounted on the ceiling or on the walls. So anyway, this is irrelevant. So this is the shoulder, then the elbow, and then the prismatic joint and the revolute joint, they are coincident. Is exactly that case. Now, question. Why I'm saying that the prismatic joint comes before the 4th revolute joint and not vice versa? Who tells me that this is the 3rd joint and this is the 4th joint and not vice versa? It's a chain. So I should say, if a joint is labeled first of another one, it means that there's some link which is moved by this joint, but not by the 4th. Otherwise, it would be the opposite. Okay? So if I'm rotating joint 4, this is rotating. If I'm translating joint 3, this is going up and down, but this is not rotating, so this comes after. Still, this question is academic. Why? Because you could interchange the order, even if physically you have this sequence. Why? Because this is a rototranslation around the same axis, and we have just learned that we can interchange the order, we obtain the same thing. Okay? It's a special case, but still worse. Now, the fact that all joint axes are parallel already tells us that there will be no twist, no special twist between the joint axes. So the alpha angle, which are constant, which characterize the twist of the joint axis, will either be 0 or pi, why 0 or pi and not just 0? Because we can change the z-axis. No? If I write here all zeros, I know that all z-axis will either go upwards or go downwards, from 0 to 4. If I have some pi, it means that at some times I will have a flip. And this is done not for making things more complex, because have you seen the Denavit-Hartenberg matrix? This contains sine and cosine of alpha. So if I write 0 or pi, the sine will still be 0, and the cosine will be either +1 or -1. But so it's not big complexity of changing these things. Okay? So this is the first step. The second step, look at the link axis. Now, common normal. This is link 1, joint 1, link 1, joint 2, common normal. These are parallel. There are infinite common normal, but the A1, the length of the link, is uniquely defined. So I can place the x1 axis at which level I wish, but then when I compute A1, it's this distance. It will carry a sign depending on how I choose xi, but I mean, this is defined. So I'm just placing generically here. Same thing for A2, joint 2, joint 3, parallel, the common normal are infinite. I'm choosing any one, and I compute this distance, and this will be A2, and then I will give a sign to this distance, and it will become a displacement, depending on how I'm choosing the xi axis. A3 is certainly 0. Why? Because joint 3 and joint 4 are coincident. So there's no distance, no matter how I compute this. Okay? And then A4, you will see that depends on how I choose the last frame, which is the nth frame, frame 4. And I know already that there is some ambiguity in doing this, so I'm not writing here A4 yet. Now I put the frames, and I will put now frames in such a way that I don't introduce any displacement. I can even reduce what I will do, but just for illustration, I'm keeping some non-zero parameters. But what I will certainly do is to place the two link axes at the same height, no matter which one, but it's the same height, because it's useless to move it up and then move it down. I mean, why doing this if I can place it at the same level? In my arbitrary choice, I make the most convenient one, which zeros some parameters. Okay? So I start with base frame. This has some ambiguity. So the origin and the x0 axis are arbitrary. What do I mean by that? That this will certainly be z0, and I'm choosing now upwards. Why? Because this is on the floor. I want to compute positive z in the air, not in the concrete. So zeta 0 will go there. Arbitrary x0, which means that I can choose this like here, or whatever x is on the floor. And if this is mounted in this room, I would choose x0 along, I mean, parallel to the walls, just for convenience. But you can do whatever choice you wish. Not only x0 is arbitrary, but its origin is arbitrary. It means that you can place this here, so really on the floor, or just, I mean, after this step here, or even here, or on top there. It's not relevant. Any choice is feasible, but of course, since everything will be defined in terms of this frame, you choose this frame so that you understand when you have a position where the end effector is. If you place it in the air, over the top, you will always see negative value of z, for instance, which it's okay, but I mean, confuses only things. So we are placing, just for illustration, this really on the floor. And x0 is some arbitrary decision. y0 completes, and from now on, I will not show the yi axis just because they complete the right-handed frame. So this is theta 0. Now, frame 1. I have to put Z1 on joint axis 2. Joint axis 1, joint axis 2. Z1 is here. Okay? Remember that this frame is attached to link 1. This is why it has indices 1. Okay? So I'm choosing Z1 going up. I could choose Z1 going down. It's irrelevant, but why should I twist by pi this? So I will, choosing it that way in the same direction of Z0, I will have alpha 1 equal to 0. Okay? And then x1 is along the common normal. Typically, these choices, I could choose this or that one, but I tend to, as a rule of thumb, to progress toward the end effector. Okay, so I'm choosing x1 like this. Why do I put the origin here? Just because I've chosen this common normal and not this common normal. If I had chosen this common normal, I would have put x1 here and the origin here. Okay? So look at this. For going from this frame to this frame, what are the elementary operations that I do? I translate along zeta 0 up to this point, and this will be the D1 constant parameter. Okay? A translation along zeta 0. Then I have to rotate from x0 around zeta 0 so that x0 is aligned with x1, so here, and this will be theta 1, the joint variable. If I move this, I will change the theta 1 variable. Then I translate by a constant parameter A1 along x1, and this is the length of the link, and A1 will be positive. Why? Because I'm going from here to there in the direction of x1. This is why it's convenient to choose x1 like that and not the opposite, so that I have a positive number there. Okay, and then no twist because alpha 1 is 0. Okay? So, this is frame 1. Same thing for frame 2. Again, zeta 2 along joint axis 3. This is the prismatic axis, but also the last revolute axis. And I choose the same orientation, so direction, so that I will have another alpha 2 equal to 0. Then I have chosen the common normal at the same height of this, so that x2 will be chosen in the same way. And this angle between x1 going to x2 around z1, so around joint axis 2, will be theta 2, the second joint variable. There will be an A2 positive for going here. There will be no D, because these are at the same height. No D parameter, so D2 equal to 0. Okay? And that's it. Y2 completes the right-handed frame. How many more frames do we need to assign? Up to now we have chosen 3 frames. No? Frame 0, frame 1, frame 2. How many more are missing? Remember, this has 4 joints, so 4 moving bodies plus the base body. The base body has frame 0, so we need to assign frame 1 attached to link 1, frame 2 attached to link 2, frame 3 attached to link 3, and frame 4 attached to link 4. Which is link 3? Link 3 is this metallic part that moves up and down. So it's really, you cannot see, you cannot touch it almost. It's always inside this box. But this is link 3. And link 4 is whatever is attached here. For instance, if you have a gripper mounted there, then you see link 4 is the gripper, which is the end effector. Okay, so we need 2 more frames. Now the third frame, this is multiple arbitrary because it's coincident, no? So I can choose the origin of this frame where I wish. So zeta 3 here is taking it along joint axis 4. So coincident and same direction, because I don't want to put a pi there as an alpha. Alpha 3 is still 0. Then the origins of frame 3 can be arbitrary. Now I place it here because so I can trace exactly the position. And this will be the variable, because if I move up and down joint 3, this will go up and down. Frame 2 remains fixed, but frame 3 moves together with link 3, so goes up and down. So this distance between x2 and x3 along the joint axis is the D3 variable, which will be the joint variable Q3. Okay? And now in this configuration, for instance, D3 or Q3 is positive or negative? It's this distance, huh? Only it carries a sign, so it's positive or negative?
It depends on which frame we want to make.
No, it does not depend on anything. You have already the frame, so now you should tell it. It's negative, because you're going from this origin to this origin. You don't need to do a displacement A. You need only to do a displacement D, which is a variable, and it's variable D3 because it's joint 3, and you're going from here to there in the opposite direction of the joint axis. So this is D3, not minus D3, it's D3 equal minus 10 centimeter. Okay? There's another thing that we have chosen here. Remember, now there's no angle between x2 and x3. But this is my choice, because I could have chosen this frame with the x3 axis rotated by 32.5 degrees. And this will remain constant, because this goes up and down, and this angle stays the same. But why should I choose some strange number? Then I have to compute sine and cosine of this angle, while I can zero it or put it at 90 degrees. I mean, these are the standard choices. It's arbitrary, but I choose the most convenient one, 0. So I align x3 with x2 because this is a prismatic joint, so there will be no changes of theta in moving this joint. Okay? And finally, suppose now, just for showing things, suppose that here you mount some tool that ends here. Now, the last frame, the only thing which is defined is x4, so xn in general, which should be intersecting orthogonally the last defined joint axis, which is z3. So x4 needs to be chosen in this way, one of these axes. But I can put it where I wish, and now I'm putting it here just to show that there is some displacement. And imagine that here there is this tool ending here. So this is why I've chosen the origin of frame there, just to put it more in evidence. And then I've chosen the other frame, the Z4 is arbitrary. It should be orthogonal to X4 because it's a frame. And now I'm choosing it in this way. I could choose it at any angle, but I don't want to introduce a strange angle there. So either I choose it like the previous Z, so I will have alpha 4 equals 0, but I flip it down, so I will have alpha 4 equal pi, just because this is the approach direction. So this frame 4 is similarly to the end effector where the z-axis should approach things in the previous slide, just for illustration. And that's it. I've done. So this is the explanation. And now, since I have assigned the frames, I can compute the table of DH parameter. Pay attention. They always go together. If I give you the table, you should be able to place the frames. If I give you the frames, you should be able to place the table. Okay? Because they are defined in the same, according to the same notation. So you can read this table by rows or by columns. The table has 4 rows because the robot has 4 joints, and so there are 4 homogeneous transformation matrices. And it has always 4 columns because these are the 4 parameters So this is by chance a 4x4 matrix, apart the labeling in blue. Okay. If the robot was the KUKA 7R robot, it would have 7 rows and still 4 columns. Okay. So what do I see here? I see it's easy. It's easier now to look them by columns. Yes, by columns, so by parameter. Although we have defined frames one after the other, so we have built this by rows. Okay. But if I look at the alpha parameters, I recognize that zeta 0 has the same orientation. I mean, they are all parallel, but now zeta 0 has the same orientation of zeta 1, so this is a 0. Zeta 1 has the same orientation of zeta 2, so this is a 0. Zeta 2 is the same as zeta 3, a 0. Zeta 4 had flipped down, so this is a pi. Pay attention, plus or minus pi? Well, it depends if I look from x4, if this has rotated clockwise or counterclockwise. But the result is exactly the same. In fact, you can place plus pi or minus pi, you obtain exactly the same matrix. So it's usually better to put plus in this case, but this is just for the matter of eliminating a sign. Okay. Now, the A, remember, A and D of the same index are the two displacements, only the displacement that goes from one origin to the other. One is a displacement along zi minus 1 and the other along xi. So if I look at these two, I move, so this index is I1, so I move along zeta 0, and this is D1, and then along x1, and this is A1. Okay? D0, A1. In this case, both positive numbers. I don't put a sign here, but these numbers, if I put numbers, and now I have to measure things, these two numbers will be positive, because I'm moving in the direction, positive direction of zeta 0 and in the positive direction of x1. Now I'm at this point of the origin, so I look at this second combination. These are the displacement that I need to make for going from origin 1 to origin 2. And this displacement is along z1 and this along x2. So from here along z1, I don't have to move up and down, so d2 is 0. I only need to move along x2, and then I have an a2 positive because I'm moving in the direction of x2. And then I've reached this origin. You see that it's nice to separate things. Same thing for going from origin 2 to origin 3. I have these two quantities. I don't need to move along x3. I just need to move along z2. And this will be a d2, but this is the variable. So I will put the q3 here, because this is changing. This is the prismatic joint. And finally, for going from this point to this point, I only need to move along, not z4, along z3, and then along x4. Along x4, I don't need to go out. I just need to move along z3, and so I will have a d4 parameter. And since I'm moving in the opposite direction of z3, this number will be negative. Don't be confused by the fact that z4, because you're moving around z previous and x current. Okay? Finally, the last column, can I look at the variables? Well, there are x I minus 1 to x, rotating around zi minus 1. So x0 to x1 rotating around zeta 0 will be theta 1, which is a variable, so q1 is a variable because this is fixed while this is moving with the first joint. Okay? Then x1 to x2 seen from the z-axis on joint 2, so z1, this will be theta 2 and will be another variable. So this is q2. From x1 to x2. In this configuration, this is positive or negative? Negative, because x1 to x2 seen from zeta 1, it's clockwise, so this is a negative angle. I don't put a negative sign here is Q2, which is negative in this configuration. It's a variable, so it may become positive if instead of having this left hand configuration, I will stretch and then go there. So it's like going with the right handed. And then it becomes positive. Okay? There's a 0 here because this is a parameter, but joint 3 is prismatic, so theta is a constant. And in fact, the fact that we have a line x2 and x3, this was our choice, puts a 0 in this place. And finally, Q4 is along Z3, gives the position. This is theta 4, it's a variable, so it's the angle between x3 and x4. As seen from the joint axis. The joint axis is fourth joint axis, so it's Z3. So I'm standing on top. I see x3 going almost 90 degrees over x4, but rotating clockwise. So this value in this configuration will be minus 90. Okay? So now I have the table. I have the standard Denavit-Hartenberg matrix. I put the rows of this table into the associated homogeneous transformation matrix, and I do the product. Oh, just a note. In this case, I've done this for presentation. D4 is negative. We have already commented this. But we could have chosen the frame in such a way that we could 0 D1 and D4. These are, in reality, inessential parameter. Why? Because I could move frame 0 from the bottom to whatever height I've chosen for the link axis. So if I move this here, then I will 0 D1. Okay? It's good. So I will have a table with D1 equals 0, but I'm defining everything with respect to a frame which is now not at the bottom of the floor, but somewhere here. Okay? And similarly, if I move this from here to here, I will 0 D4. Well, and one should say, well, but if I 0 D4, I should have the end effector, my tool here. I've placed it here because I've said, well, I have a tool which is this big, and this is exactly where the tool tip is. Correct? But this is not really a matter. In fact, people prefer to put the frame here because this frame is forever, while the tool can be changed. I can have a tool which is this big or a tool which is this big. Should I change every time the frame? No, I don't change the frame. I place the frame here, and then I define the position of the tip in frame 4 according to the tool center point of this tip. It's a big tip. I will look for a position in frame 4 which is far away. If it's a small tool, I will look for a position in frame 4 which is closer. But the transformations are always the same. I know a vector in frame 4, and then through the chain of product, I will know the position of this tip in frame 0. This is exactly what we have introduced homogeneous transformation for. So if I substitute into the generic ai minus 1I as a function of qi, the first row of the table leads me to this structure, the second row to the second homogeneous transformation, the third row to this one, and the fourth row to this one. Now, never forget, because you can do this by hand, or you can do this by MATLAB in symbolic manipulation mode. Okay? But no matter how you do this computation, don't switch off your mind and just look at these matrices and see, do they make sense? For instance, what is the first matrix? What can you read in the columns of the first matrix? First of all, you see that this is an elementary rotation around the z-axis, the current z-axis. In fact, the first joint is a rotation around zeta 0. And theta 1, which is q1, actually, is exactly defining that way. So the rotation part makes sense. What is the last vector? The last column? A1 cosine theta 1, A1 sine of theta 1, and D1. This is, pay attention, no translation. It's the vector going from origin of frame 0 to origin of frame 1, expressed in frame 0. Okay? So it has a z component, which is exactly the D1, and this is constant. Then it has to move by A1, but since the link 1 is changing with theta 1, this length is divided by sine and cosine of this angle, as seen from the frame 0. Okay? If I write the same vector, pay attention, the same vector from origin to origin in frame 1, let's do this exercise. If I'm writing this vector going from here to here, in that matrix is expressed in this frame. Now I want to express it in this frame. Since this frame is rotating with theta 1, this will be just D1 along the z direction and A1 along the x1 direction. There's no y1 because I'm moving with the frame, which is moving with the link. So when I'm on board of this, I see a constant vector for going to the origin 0 to this origin 01. Maybe this is confusing at this point, but think about it. So, and same thing. This is exactly the same as before, only with two theta 2 in place of theta 1, and there's no D2 because now we have moved up to this level and we remain at this level. But otherwise, it's exactly the same. This is associated to the joint, prismatic joint. In fact, I don't see any rotation here. It is always like this. When I have a prismatic joint, I will have an associated Denavit-Hartenberg matrix, which is the identity in the rotational part. No. It's the identity if I have preserved the same orientation. If I have changed things, I may have a permutation of the identity, or it's constant. This is true. It's constant, but it's not said that it's exactly the identity. And here I see the only variable, D3, which is Q3, in fact. And finally, this. And in fact, you see here, it's very clear that this is, again, a rotation matrix. It's around the z-axis. But it has strange things. It has a -1 here. It has a minus sign on the diagonal on the cosine. It has plus and plus here. It's really not like this one. Why is this? Because from frame 3 to frame 4, I've done this flipping. And the parameter in the table have taken into account of what happened. Of course, this is a rotation matrix and represent the orientation of a frame, of a right-handed frame with respect to another right-handed frame. In fact, it has determinant +1. Only it has these strange things because we have flipped things, the z-axis essentially. If we had kept all the z-axis pointing upward, I would have had here the same structure as this, only with theta 4 in place of theta 1 or theta 2. Okay? So, and now, this is the Q's, of course, like we defined. And I start doing product. For instance, I do the product of A01 times A12 times A23, and I get this one. Then I have A34. And if I do the last product, this is what I obtain. Of course, you can do the product in the right order, but you can group things the way you prefer. Okay. Now, what do I recognize here? First of all, I'm calling this A04 also TBE because in our case, we have placed the base frame coincident with the 0 frame. So we have placed the base frame exactly with frame 0 at the base of the robot. And I've chosen Z4 in that direction so that even the last constant transformation between frame 4 of Denavit-Hartenberg and the end effector frame, which has the z-axis in the approach direction, is the identity, so no changes. They are coincident. Okay, it's a 4x4 identity, by the way, remember. So, this is my direct kinematics in the form of a homogeneous transformation matrix. And here I recognize the position of the origins of frame 4 or frame E, in that case, expressed in frame 0. And here I recognize also a rotation matrix, and with the n, s, and a axis of this rotation matrix as a function of the variables. And pay attention, you don't see, while here you see Q1 is here, Q2 is here, this is cosine of Q1 plus Q2, Q3 is here, you don't have Q4 here. In this, you don't have Q4. Why is that? Q4 does not affect the position of the origins of frame 4. In fact, the origins is there, it's moving up and down and moving like this. But if I rotate the last joint, the origins doesn't move. So this is a function only of Q1, Q2, Q3. In a similar way, the orientation of the last frame is only a function of Q1, Q2, and Q4, not of Q3. Why? Because this prismatic joint going up and down doesn't change the orientation of the end effect. Change only the position of the origin in a very simple way, see, linearly. Changes the z coordinate of this point. So this is one way of writing the direct kinematics, but we have mentioned that we can extract things. So let's write the same as a task vector. What we do is we extract from the final homogeneous transformation matrix what we need. And for instance, this is just an example. We would like to have the 3 coordinate of the origin of the point, the final point of the robot, and just an angle around the z-axis, an absolute angle. In fact, it's a planar problem only with this plane going up and down. So this angle is like this, and I hope I've done things correctly here. Now I have Q1, Q2, maybe it's correct. So these 3 components are simply taken from the last column of the homogeneous matrix. So I take this is the position, so I organize it as R1, R2, and R3 of a vector R. It's just saying the coordinate of the origin. And then the last element require a little bit more cautious. In fact, I'm not sure that I've done things correctly. So I'm extracting from the R matrix this angle. This is almost an elementary rotation matrix around the z-axis, only that we have this flipping. If we didn't have this flipping, that matrix would have looked like C1 to 4 minus C1 to 4, C1 to 4 plus C1 to 4, and a plus 1 in the position 3, 3. Then I'm sure that extracting this is just extracting the argument of this cosine and sine, so the sum of Q1, Q2, Q plus Q4. I suspect that there should be a minus here, but I'm not sure about this. Okay, I may go back and check. Okay, but you see the essential. So you extract what you need, and you have organized this in an array which is M equal 4-dimensional, rather than a matrix which contains 12 elements, 16 elements. 4 of them are always 0, 0, 1, so 12 actual elements, 9 are the rotation matrix, and 3 are the position. So you have a more compact expression. So I think that we're almost done, and the following are just exercises left to your desire, if we can say so. So, for instance, this is the Standford arm. It's a 6 degrees of freedom robot, one of the first developed for research purposes, which has the first 2 revolute joints, so rotation around a vertical, and then elevation of the shoulder, but the shoulder is offset. You see that it's on the side. Huh? It's not aligned with the first axis, and you should take into account this. Then the third joint is prismatic, it's going up and down. And then the last three joints have joints that intersect in a common point, so they have a spherical wrist. So the last three revolute joints are such. So this is 2R, P, or 1P, 3R with spherical joint. So if I give you this picture where the frames are already assigned, you see that all the frames are there. So what you can do is not to assign the frame according to Denavit-Hartenberg, but just check that this assignment is correct, because you may have assigned frame which cannot be covered by the notation of Denavit-Hartenberg. Just because for going from one frame to another frame you're doing, for instance, you need to move along the y-axis, which is never the case. So that means that the frames are placed in an incorrect way and cannot be captured by the table of Denavit-Hartenberg. So you have to check this. But assume that this is correct, and you can check if this is correct. So with this assignment, you can determine the associated parameter table. So you do exactly what we have done before. Or I can give you the table and ask you to place the frames according to that table. Then from that you can compute the homogeneous transformation matrix and then the direct kinematics. And then as an exercise you can write a code which computes this numerically. So these are transformation matrix that you evaluate with numbers. So in a given configuration with given data of the constant parameter. So the length of the links are included there. And so you can compute numerically some output. Or you want to have the symbolic expression like we did before. And in that case, you need some symbolic manipulation toolbox. And I think that at this moment, I would show you this program, which is available on the website. This is exactly the symbolic computation of the direct kinematic that we have done by hand, made with a program and applied to the case of, okay, let's, so I will skip this, but essentially you define symbolic quantity alpha, dA, and theta. Then you assign symbolic values or numerical values 0, pi to some of this. For instance, I am not assigning a numerical value to A1 and A2. This will be the length. I don't put a number there. Okay? And then if I run this, and it will ask me to change folder, of course. And now he's computing things. So you see that he computes transformation matrix. First the A01. This is already A01 times A12. You can recognize it by Q1, Q2. This is multiplied by A23, and you see that Q3 is here. And now the last step is taking a while for doing the simplification. Because I've added in the program some simplify, so that if they have a trigonometric expression, they try to simplify as we do by hand. So it's taking some time. It's still busy. And this is an easy case. So pay attention. Don't think that you can modify this. So here it is. You can modify this code to write the direct kinematic of any robot with no matter how many joints, and also with no matter complex tables of parameter, of Denavit-Hartenberg parameters. But if you run this blindly, you can stay, I don't know, forever. At sometimes your computer will go in trash because it had to take, if you ask to simplify things, it will take forever. If you don't ask to simplify, you will have huge expressions which apparently are very complex, but with your experience could be simplified. So use these tools with caution. This is why doing incremental simplification, don't compute everything in one step and then try to simplify, because the tree of possible simplification that the system builds is exponentially exploding. This is why it takes a lot of time and may also not even get to a result. But now, this is now posed. This is exactly the matrix that we have found before. You recognize the rotation matrix with the -1, and then the cosine and sine, but with the minus on the diagonal, and the sine both with positive signs. And then here, the last position with D1, D4, which are constant, and Q3, which is variable. And then the other A1 and A2, which characterize the Px and Py position. And out of this, these are, sorry. Okay, now I'm just extracting from this matrix the last column, which is the position vector P, or the 3 columns of the rotation matrix, the N vector, unit vector, the S unit vector, and the A unit vector. And in fact, the A unit vector is Z4, and it's 0, 0, -1, because it's always pointing downwards. In frames 0 is always pointing against zeta 0. So it's 0, 0, -1. So again, you interpret this in a nice way. Okay, I think that this is done. And if we go back to this one, we can, this is the solution of what I was asking. So this is again the same picture as before. And here you find the table built from this frame. Again, I stress this fact, they go together. And in fact, sometimes you say, well, I just need to have the table. I don't need to have the frames. Why? Because with the tables, I compute the transformation matrix, and then I compute the directive matrix. Why should I need to have the frame design on the structure? Well, if you don't design the frame on the structure, you don't understand what you're doing, if your results make sense or not. Okay, so this is why I'm insisting that you have to do the two things together. And also because there are some options in choosing the direction of the various axes, and if you don't figure out what is there, you don't see if I'm rotating a joint in the positive direction, in the negative direction, so you need to have the frame also placed. So I'm not commenting this, I leave you this for your use, but you can check this. Well, let's look just at the alpha, at the twist of the z-axis. So I have z0 here and z1 here. Now z0 rotates and goes over z1 as seen from the common normal, which is the x1 axis. Since this rotation with my head on the arrow is clockwise, this is a minus pi over 2. Okay? Then I have zeta 1 and z2. So here I'm rotating like this. X2 has been chosen in this direction. So this is 90 degrees in the counterclockwise, so it's pi over 2. Then I have z2 and z3 on top, which are aligned. So I have a 0, and so on and so on. Look always at the right x-axis around which you have to rotate. Similarly for the theta, look at the right z I minus 1 axis placed on joint axis I to look at the sine of theta I. Okay? And here, last thing that I want to comment, these are number constant. These are red numbers, are variables. And in this particular configuration, I can put a number to this value. Because this is now, some parameters are always constant. So they are here. Some numbers, I don't know exactly the numbers, but I know that this number is positive, and it's just the distance from the base to this shoulder axis. I go to the robot, I measure this, or the manufacturer provides me this number, and this number is very accurate, but not completely accurate. If I'm missing a tenth of a millimeter there, this will be reflected in the chain to some error in the end effect. So I have to calibrate this number. But nominally, they are okay. So, but then the variable in some fixed configuration, this is just geometry, so I can look at the values, and here, this is why I'm adding an equal here. Here I cannot add an equal because this is just this distance here, and I don't know this distance. An angle, I can guess the angle, 0 pi over 2, but this distance is a variable, and I just can say that in this configuration is a positive number, and so on. Here I have put values for this particular shown configuration of the robot. Otherwise, these are variables. Okay? And we conclude here, and the last 2 slides are just open exercises, and they refer to the 2 robots that we have in the lab. This is the KR5 Sixx XX. It's a 6 degrees of freedom, all revolute joints with a lot of offsets. Look, this is the rotation axis of the base, around the base. This is fixed, so this is moving. And this is the shoulder. And you see that the 2 axes are like this, so they don't intersect. They have this offset. And then there is another offset here. This is the rotation of the elbow. Okay, and this does not intersect with one of the 3 axes of the wrist, which is above and does like this. So you have these 2 offsets in the structure. And these are associated either to A or to D parameters. So pay attention. This is a very common architecture. Okay, because why there are these offsets? Because you can place a motor here, then you can have a transmission. It's convenient to have this displaced. And similarly here, you have a motor, and then you have some internal gearing so that you transfer the motion to the following links and so on and so on. Okay, so here the exercise is assign the frame, and you can have multiple way of assigning frame inside the Denavit-Hartenberg convention, because you can choose the direction of the z-axis, the direction of the x-axis, and so on. But once you have chosen the frame, you have a unique association of a table, and vice versa, of course. And then from there, homogeneous transformation matrix, and if you wish, using the code or doing it by hand, and compute the direct kinematics. And for doing this, it's very useful to have this draft, because on the draft you see also the numbers that you need, and it's good exercise to recognize which numbers are the one that should be used for the direct kinematics. And finally, this is the lightweight 4. This is much more nice structure, because there are no offset at all. This has a spherical wrist, but also a spherical shoulder, plus an extra elbow axis, which is here. So in fact, you will see, if you do the same operation, assigning frame, blah, 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 you will find that you need only 2 numbers to characterize the kinematics of this, because you can place the 0 axis at the center of the 0 frame at the center of the spherical shoulder, the end effector, the last frame, at the center of the spherical wrist. So the only 2 kinematic numbers that you miss, since there are no displacement, are the distance between this point and this point, and between this point and that point. 2 numbers are all the kinematics that you need in nominal condition, provided that those axes are parallel or orthogonal exactly. Okay? This is why this design is so clean. This does not mean that the resulting expressions are simple. They are huge, but still only with 2, let's say, numbers, non-zero numbers. Well, I think that this is it. I have an appendix added at the last minute, but this is just a warning. You can also skip this appendix, because this is an alternative, also called Denavit-Hartenberg convention, used in some books, in particular in an American book by John Craig. And there are some papers written assuming this notation. And there are slight differences, but you get lost if you don't know that they are using this Craig modified version of the Denavit-Hartenberg convention. We prefer to use the classical one, And here I try to illustrate some simple example of the difference in allocating frame according to the two convention. So if you don't encounter this, just remove this appendix. If you ever happen to find a strange transformation matrix which contains both I index and I minus 1 index, this means that this author is using the Craig's notation, and then you have to take care of it. Okay? But we will always use the classical Denavit-Hartenberg rotation. It's like having a standard. No? The standard may not be the best one. In some situation there could be something better, but since 99% of the people is using this, or 95% of the people is using this, you use that so that you don't want to live isolated on an island and do your own work by yourself. Okay, thank you. This is done for this topic. On Monday, we will go back to some exteroceptive sensor description for robots. Bye-bye.